Hello guys, so welcome to in-class practice for week 6. I'll be covering that, and so let's get into that. Um, I have the key here downloaded in Excel format, so I'm gonna be doing most of the work in Excel sheet instead of the Google Sheets, because most of you guys are using Excel sheet and I think it's also useful because there are some functions which are available in Excel only and they're not available in Google Sheets. So I would suggest that you guys try to do it on Excel. I think you did the earlier practices on Google Sheets, so it's a good thing that you get a taste of both. So if you see here, the data is very similar from week 5. It's the same data. The military expenditures collected by SIPRI for 10 years for each of the countries we have. And this time we'll be using the hypothesized column also. But if you look, we were just using the country stats from the last sheet from the last time when you created this pivot table. And um, so let me actually convert this into currency. So it's better to understand. But yeah, we are essentially doing this created this pivot table, and I would say try to create this on your own so you have an idea. Uh, it would be a good exercise for you. So we're using that. I'm not gonna do show you how to create the pivot table again. But so what we basically are going to do is question number one, calculate the standard error for average military expenditures for the last 10 years. And the formula for standard error is standard deviation divided by square root of n. Um, and so we have the standard deviation in the country stats. So if you go down here in the grand total, for every field, it calculates the total of that field according to that field. So if this is a minimum field, it's gonna calculate the minimum field. It's gonna find the minimum of this whole values, right? And in the grand total, so that's zero. The maximum of these all values, which is 814. And when it's average, is going to take the average of all these averages, right? And then standard deviation is going to take the standard deviation of these standard deviations. So that's good. Even though it says grand total, it's not a sum um, of these values. So the formula here is standard error, standard deviation. So you can pick the standard deviation from country stats, which is this value, and divide by uh, square root of um, the values. So we have the values here to count. Basically, that's what we want because all these values, the count is 10, right? And we are adding those up. So it's basically 15, 30 values we have. And so we can pick it from here instead of doing the number of rows or, but yeah, make sure that the count is of all the values because even though in this you will see just um 153 rows, but if you go to the original data, you can see that the data here there is different, right? So it's a square root of n, which is like the all the observations, right? So that's your first. That's going to give you the standard error, and so that's your standard error, and so you can use that. Then question number two, calculate a 95% confidence interval for average military expenditure for the last 10 years. You find the confidence interval by the plus minus of the confidence interval from the mean. And so we want to find the confidence value, the lower bound for 95% and upper bound for 95%. So the confidence value, if you go here, it functions. So that was question number one. There's a formula that you can use for confidence values. Confidence T, it will give you the confidence value. 95% confidence value. Um, so you use that formula, and if you come here, let's do that again. So you want to find the confidence value, and that value is confidence E. So confidence dot T. So what it wants is alpha, standard deviation, and the size. So alpha is basically your confidence interval value. So if you are trying to find 95% confidence interval, your alpha will be 0.05 because 0.95 minus 1. So 0.05 is your alpha, right? So you're gonna give that. Standard deviation, you're gonna pick from again from here, country starts. And then finally the count, the number. I mean, let me check if it, uh, okay, I know. I think it's the count. Let's see. Three functions. Yeah. So basically, yeah, that's the count. So if we here, I had the formulas from the last table, so I think there was like some. Um, yeah, so that's your confidence value. And I think I downloaded the sheet from a sheet, and some of the formulas are messed up. So I'm going to correct that here in Excel. But the answers values in the Google sheet should be correct. But I'll show you again. So this is your confidence value, and basically what it tells is that your 95% confidence interval means that this value, like the 95% confidence interval, is situated between from the mean, um, plus minus this value from the mean. So this is your you pick your mean. So your confidence, so your lower bound is your lower bound is the mean minus this value. So you can pick the mean from country starts here. That's your mean, average. Yeah. And minus, you already have the value here for confidence value. So that's your lower bound. And then your upper bound of 95% is basically mean plus. So you can use this formula pretty much. Mean plus. That's your upper bound. Let me fix this. 159 and this should be 150. Yeah. So these are your confidence intervals. And basically what it tells is that with how much confidence you can say that your mean is situated between these values. So 95% of the time, if you randomly sample from this population, the mean will fall between these values, between these two. So you're trying to find the confidence interval of the mean, right? If you see the question here, average millet, so mean, right? So and mean is related to the standard deviation, right? So this is basically that normal distribution chart, and it's finding that 95 percentile value. So 2.5% here and 2.5% on the other side. It's excluding that, and 95% of your values for the mean should fall between these values, right? And the confidence value basically is calculated, and then you add or subtract that. So this is your confidence interval, 95% confidence interval. So there's, yeah, so this formula is useful, the confidence that you can use. Okay, so question number three, test the following hypotheses. The average military expenditure over the last 10 years is 5 billion. With the information you have, standard deviation, mean, alpha, you reject the hypothesis. So the hypothesis is this. So your null hypothesis is that the mean is equal to 5 billion. And then the alternative hypothesis that mean is not equal to 5,000. So the way you test it is, um, if you go to the function here, so this is, you do the t distribution two tail, because this is a two-tailed test, because you wanna do it from the distribution on both the tails, because you have tails on the either side. Um, so you can use that, and the way this formula works is, so I have it here. So you first find the t-statistics of your null hypotheses, right? Whatever your null hypothesis is, you're trying to find the t-statistic, right? And this is a two-tailed test. Um, because it can be lower than 5 billion, and it can be higher than 5 billion, right? Because it can be on either side, right? So that's why this is a two-tailed test, because it can be either side of the mean, right? Because you're saying mean is equal to 5 billion, right? So it could, if even if it's higher or it's lower, it's going to, the null hypothesis will be rejected. So that's why it's a two-tailed test. So you use the formula T distribution dot 2T. And if you see here, it's going to take the X value, which is your 5 billion, and then it's going to take your degree of freedom. And your degree of freedom is basically your um, it's basically n minus 1. So you had the n here at 150, 1530, so the n minus 1, right? Um, and your x would be basically your mean minus the actual mean of the distribution, minus um, the value of the mean in your null hypothesis. So that is the formula. So you do t distribution dot 2t, and your x is basically your average here, minus your null hypotheses here, that you had, that is it greater than 5 billion, or that is equal to 5 billion, right? So 5, we're gonna do 5 billion, just make sure of the number of zeros. So it should have 9 zeros after 5. So that is your x, and that divided by the degree of freedom. So your degree of freedoms is again this number, uh, minus 1, right? And let me just check something at pivot data. Yeah, so probably there's a, oh, sorry, not divided by. This is an argument. So get pivot data minus, oh no. So that's your first argument, and that's the second argument. We actually put the, your first was your average minus 5 billion. So that's your first argument. And then your second argument is this minus 1. See what was the. Oh, sorry, my bad. You need to first calculate the t statistics and then use that to find the p-value. Sorry, so my bad. So you want to calculate the t statistics, and the formula for t statistics is this: x minus mean divided by standard deviation divided by square root of n. So I have the formula here. So this is your average that we got from that country starts table. This is the 5 billion minus 5 billion. And then this is your standard deviation, and then divided by square root of the total. 159. So this is your t statistics, right? And so once you have that, now you can use this formula, and this formula basically takes the t dot distribution dot 2t, and this takes your t statistics that you have here and degree of freedom, which is your count minus 1. So your count here is again 153.0 and that minus 1. Wrong formula. Oh, sorry, you wanna take this from the pivot table. Country stats. Yep. And then your, oh, yeah, you can convert this to numbers. So you can see here that the p-value is really small, and it's less than 0.05, uh, which is our usual standard p-value. If it is smaller than 0.05, then we can reject the null hypothesis. And so that's why we can say that the mean of the military expenditure over last 10 years is statistically different from 5 billion. And you can also see like the mean is 12 billion, but we always, these means are always relative. So we have to perform this test, right? Because that's why we take into account the standard deviation. But if your p-value is lower than 0.07, 0.000071042, 0.05, then you can reject the null hypothesis, and that is what we did. Um, so yeah, and then there's another way of doing this, which is if you go here and your Excel will have this show tool pack. If you don't have it, you can add in from here and you can say tool pack. Uh, Yeah, so this is the tool pack miner. Um, and you can add it to your Excel or you can open it from here. And here you have these tests. So we are doing the test with two test sample assuming let me confirm it. Um, yeah, unequal variances, right? So that is the one we are doing. And so you can do this, and here you can put the variable. So your variable one range, if you go to the functions here, your variable one range should be the military expenditure column, and variable two should be hypothesized column. Hypothesized mean difference should be zero because we're assuming that it's 5 billion. And if the results are difficult, and then you get the results. So first, let's put our variable one range uh, from here, from our original data set, right? And this is our variable range, military expenditure. So there is some issue here. It's supposed to pick. It's supposed to pick the range here. If you go down, it should be able to pick that range here, but for some reason it isn't doing that. So what we can do is we can just probably add that manually. So we can say A7 to actually we might have to give the our sheet name also. So sheet name and this exclamation mark, it would refer to the sheet. And then from there, A7 to we can go down bottom A1536 1536. Sorry, not A, D. D. And then for hypothesize, it's the same thing. ID, and it is E7 to E153736. Sorry. And then hypothesis mean difference is zero, and then the alpha we keep it. And then output range, we want it to be a pair here, so we can just give it there. So it should able to pick automatically, but I don't know why it isn't doing that because once you click it, it should take it. But we want the answer, we want the table to appear here, right? Output range. So we will just give it question number three. Um, and we'll say E9. Okay. Mhm. Okay. That's weird. Let's see. See if I'm doing something wrong. Yeah. So you're already on the sheet, so you don't have to give the sheet name. Um, so yeah, this will give you this sheet. It might be a bit difficult to read. So first you can just convert this into some of these numbers into currency. Same here. But basically, what it's telling you, it's already calculating, your degree of freedoms, your variance, um, and um, and then the T statistics, and then um, your one tail, the p-value for one tail, and then the p-value for two tail. So we are here interested in p-value of two tail. You can see it's the same value as the p. You might see a little bit of difference because how they calculate. Um, so usually it shouldn't be like should usually there shouldn't be a difference. But maybe I missed some value or something like that. But in any case, most of the values are almost very similar. And the key here is that if you have the p-value much less than 0.05, then you can reject the null hypothesis. So that is another way of doing this, and you can either do it this way or you can do it the other way, right? Okay, so question number 4. Take a look at the raw averages for Germany and Japan. Does there appear to be a difference between the means? So if we go here and we see Germany and Japan, um, can do as we can Japan also. Yeah. So you can see their averages, 49 billion and 48 billion, very similar, right? So in question number 4, they are different numbers, but statistically, there's not a difference between two because you have, such a wide range. 48 and 49 billion look very close, but again, it all depends on the context. If your average is if your standard deviation for uh, for um, for a data set is very low, let's say it's 1 million, then this seems like a big difference, right? In billions. So it all is relative, and that's what we are going to find out in question number 5, that test the following hypotheses. The average military expenditure um, for Germany over the last 10 years, that's same as Japan's average expenditure. Can you reject the hypotheses? Uh, So we're doing the same thing here in question number 5. We have this uh, hypothesis that Germany's mean is equal to Japan's mean, and the alternative hypothesis is that Germany's mean is uh, not equal to Japan's mean. So we can again do the test here. So here we can just put the values again, and um, we can for this time we can assume that the variances are equal because they're two countries from that sample. we haven't hypothesized anything, and we say that it's similar values. So we're going to say that both of them have equal variances, right? Um, so then we do two sample assuming equal variances, and we then take the value. So variable one range, we are going to put the mean of Germany, and then variable two range, we're going to put the mean of Japan, and from there we're gonna find out. So if you go here to see the functions, um, variable one range should be the Germany's military expenditure, variable two range. So yeah, so we are going to go here and we are going to sort our not sort our data. We're going to apply the two filters here. So we're gonna just do Germany, okay, and Japan, okay. I'm gonna add Germany. So we have these two. What we're gonna do here is in question number five, the variable one range would be Germany's value. So it would be these values. Uh, and so let's put these values manually tidy. And from it's D547. And be careful that you put this value because you applied filter, right? And once we're referring back to this table, you need to pick the values from these. You can't say D7, right? It has to be D547 till here, D556. Alternatively, you can do this filter and then copy and paste this table as values in another sheet, and then you will have like D after D6, you'll have D7 and all that. So just be mindful of these rows because this is where it's referencing the data from, right? And then for Japan, we are going to have a D737 till D746. D746. Yes, right. Hypotheses mean difference is zero, and then output range, we started and then question number five. So we want the data to be displayed in E6. Voila. Yes. That's interesting. Oh, sorry, D556. Actually, I think I made a mistake. Let me try this again. Let's put here and we set the ID. Uh, This up here. So we had ID D47 to D556, right? And then output range we want at E6. So, says what? D746, and then Germany was D5. 47 to D. 556. Sorry, I think I'm just making some mistake in putting the formula and ranges. So just bear with me. Let me confirm. I think I might have made some typo or the and then output rate is here. Output in chemistry. I think yeah, this might be I think yeah, this table might be right. What I'm doing, I think I might have made some mistake here because it shouldn't be 10, because this is an degree of freedoms, so it should be 9. You do n minus 1, but in any case, like these are these are very similar results. The main thing to look here is that your p value for the two tail and the one tail both are greater than 0.05. So we cannot reject the null hypothesis, which means that the means of Germany and Japan are similar. So that is why you cannot reject the null hypotheses. And yeah, I think this value is these values are correct. I'm just gonna double check and then I'll update it on the Google Sheet key. But the key idea is that even with the slight differences, what you have to look at is this p value. If you're doing a one-tailed test or if you're doing a two-tailed test, look at the p values and then based on that you can accept or reject your null hypotheses. So in this case, we cannot reject the null hypotheses, right? And then there was a question number 5, or question number 6 also. Is your answer to question number 5 different than your answer to question number 4? Why might this distinction be of interest to stakeholders? So it's not different. We say that your answer is similar because we already said in question number 4 here that there's not difference between the two statistically, and that is what we have come to the conclusion that our p-value, the difference uh, is not statistically significant, and that is why our null hypothesis stands. So our answer is not different. So basically, that's the answer to question number 6. So yeah, that was it. I'm just going to make sure which values are correct here because I copy pasted downloaded the sheet and sometimes it messes with the ranges of values. So I'm just going to confirm that and I'm going to upload the correct values on the key in class key, so just go by them. But your results won't change much because there's not a lot of difference. It's basically happening because of these observation numbers. But apart from that, like your values are correct. So just I'm gonna upload that. But the key thing to look at is your p-value, and you can do the same thing with the other method where we, in question number three, where we calculated our t statistics and p-value, and we can do the same thing again. So I hope this was helpful, and I'm going to cover this obviously in the class. And if you have any other questions or something, do let me know.